Hello, everyone, and welcome to KITE Research Round. It's my great pleasure to introduce our speaker today, Dr. Gaetano Valenza. Dr. Valenza is an associate professor in bioengineering at the University of Pisa in Pisa, Italy, and the head of the Neurocardiovascular Intelligence Lab. His research interests include statistical and nonlinear biomedical signal and image processing, cardiovascular and neural modeling, physiologically interpretable artificial intelligence systems, and wearable systems for physiological monitoring. Applications of his research include the assessment of autonomic nervous system activity on cardiovascular control, brain-heart interactions, and effective computing assessment of mood and mental or neurological disorders. He's an author of more than 300 international scientific contributions in these fields, published in peer-reviewed international journals, conference proceedings, books, and book chapters, and is the official reviewer of more than 60 international journals and research funding agencies. Please join me in a virtual round of applause to welcome Dr. Valenza.
Thank you very much, and thank you very much for the presentation and for the kind invitation. I will speak about informative randomness in complex and neurophysiological systems, and I will give you, let's say, a glimpse of results about aging. So we will focus on an aging study for the results. As an introduction, let's start by categorizing the phenomena. Phenomena can be, let's say, generally speaking, divided in two big categories. So the deterministic phenomena, which mainly can be described with the closed form mathematical equations, and non-deterministic, also known as the stochastic, or better to say in this context, fully stochastic system, which may not be described with the closed form mathematical equations, and therefore must be characterized through statistical quantities, distributions, etc. Well, this is, let's say, the main category, but actually we have something sort in the middle. First of all, although formally within the deterministic systems, we have the so-called deterministic chaotic systems, which are systems that while they are fully described by mathematical equations, so we actually know the relationship between the output and the input, they behave, so macroscopically the output behave like a stochastic system. And then we have another, let's say, particular kind of deterministic systems, which are the systems that are deterministic, may be or may not be chaotic, but it's important because they are characterized by some sort of stochasticity. Some sort of stochasticity that may be an input, but is usually within the system. So it's what we call an intrinsic characteristic of the system. And this is actually, as you will see, the kind of system we will focus on. So the question is, among this kind of system, affective modeling, and therefore, the biomarker identification and all the consequences, which one is more suitable for neurophysiological systems? Since we are introducing stochasticity, let me say that the idea of stochasticity, or what we will call in this talk the physiological noise, is something that is quite important for the characterization of the system, especially neural and cardiovascular systems. I will tell you later in detail that the noise we are talking about is not a measurement noise. It's not something that we don't want to, because it impairs our measurement, but it's something, as I told you before, that is an actual characteristic of the system. If you search the literature, you will find a nice piece of work that tells you that actually the increased intrinsic noise may be very informative and may augment the performance The neural system and the cardiovascular system show stochastic behaviors, and actually this randomness has been demonstrated to be involved also in the perception and the movement task. So let me give you a more pragmatic example of what you're talking about. So I started by giving a very, very quick introduction about the cardiovascular dynamics. You know, we have the heartbeat dynamics that is regulated by the parasympathetic, so the vagus nerve, and the sympathetic nervous system. Their concurrent action defines the interval between two R peaks, and an R peak basically corresponds to a ventricular contraction. There is also, of course, a central control, but basically what we are interested in for the estimation of the neural autonomic activity is the RR interval dynamics. So you see, this is these are 4 exemplary recordings of this series, heartbeat dynamics, also known as the heart rate variability series. And you see that when there is no variability, or if you want some regularity, it's something that is associated with important pathologies like cardiac heart failure. But you see that if there is too much variability, or if you want underlying noise, this is bad as well, because there are other pathologies like atrial fibrillation that are associated with this kind of behavior. So to make the long story short, we should have some stochasticity which must be associated with the specific dynamics. So let's try to characterize the cardiovascular system, or if you want, the neurocardiovascular system, as a fully stochastic system. So if we believe that the system is fully stochastic, then we must characterize this series and therefore the associated pathologies with some statistical features that derives from the distribution mainly. You may characterize, you know, the first or second moments estimators, so the mean and standard deviation. And actually, you know, the standard deviation of this series, which has been known as heart rate variability per se, a reduction in this variability, so in the standard deviation, has been associated with quite a large number of diseases. In fact, about 3 decades ago, this has been proposed. This was proposed as an actual biomarker of impaired cardiovascular function. What was the issue? I mean, why nowadays we don't have heartbeat dynamics as a standard clinical monitoring? Well, because it has quite soon been realized that the statistical variations you might observe in physiological state changes might be similar to some other state change in pathological conditions. For instance, there is a similarity in the first and second order statistics in this series when some healthy subjects perform some postural changes, or when cardiovascular health failure, congestive health failure patients go and are monitoring on a structured activity. So this is what we call non-specificity of this specific cardiovascular dynamics, and therefore the characterization as a fully stochastic system, while it's important, does not lead to a clinical application. So together with the stochastic modeling, there has been a lot of studies that complemented this approach with an approach by considering the system deterministic. So if you consider the system deterministic, you may want to study the system oscillations, and so characterize the frequency bands with the power associated on it that are characteristic of the system. And this has been a very nice piece of study. But if you consider it deterministic, then you should account also for the linearity or non-linearity of the system. And in this nice review, it has been demonstrated how the cardiovascular system is actually nonlinear, meaning if you have a concurrent vagal and sympathetic activities, they do result in a nonlinear behavior. And this is also evident by the saturation effect of sympathotonic and parasympathotonic activity. So the saturation of the heart rate. So this deterministic approach led to these important discoveries of definition of power bands, the nonlinearity of the system, and then the approach was complemented by what we call physiological complexity. What does it mean? It means that the cardiovascular system comprises many multiple feedbacks. So there are a lot of feedback that other systems attach to cardiovascular dynamics for regulation. It means, methodologically speaking, that the system should be characterized by a mathematical object that is called the phase space. And one way to quantify the behavior and characterize the behavior of the system is to take two different parts of this phase space. So basically, if you imagine to know the equation of the system, you may take two different initial conditions, and then you study the divergence of these trajectories. If they diverge, then the system is called complex, and in general is called also chaotic. There are quantifiers for how much these diverge. For instance, this is one of the most, let's say, basic assessment where this lambda is called Lyapunov exponent. So we fall in this category, we fall into the deterministic chaotic system. As I told you before, these are systems that are deterministic, so they are characterized by closed form equations, but they behave like a stochastic system. So this in the 90s, I would say this actually was very promising, a very promising approach. Let me give you an example of a simple chaotic system. This is a paradigmatic example. It's the so-called logistic map. You see, this equation is very simple, is nonlinear. This is a very important requirement. If there is, if the system is linear, it has been demonstrated, it's quite easy actually to demonstrate that it cannot show chaotic behavior. So you see that this simple equation, nonlinear equation, for this value of parameter, it has a chaotic behavior. While if you decrease it to 3.5, you have a regular dynamics. This is what is called the bifurcation plot, in which you have the dynamics that you know is regular, or in these phases that is chaotic. So as I told you before, this approach seemed very interesting, and a lot of enthusiasm got into the chaoticity of cardiovascular dynamics. Also, you know, the important journals got interested in this kind of approach, and therefore it seems like a venue of a new era of biomarkers in which loss of cardiovascular complexity may be associated with the pathological states. So something that might be more specific to pathology than a standard statistical approach. Then, you know, specific literature came out here in 2015, has been published a very nice review of a lot of the quantifiers of complex dynamics that might quantitatively assess this kind of behavior. What is the issue with this behavior? What is the issue with this kind of assessment? Well, those metrics, all these metrics that are based on the phase space assessment, they are all very sensitive to underlying dynamical noise. In other words, if the system is actually nonlinear, and deterministic without any stochastic input, then we may perform a chaotic assessment. Otherwise, if there is some stochastic input or dynamics, in other words, we may not assess chaoticity. So this is basically what happened in 2009. In 2009, there was a special issue in the journal Chaos. And basically, the question to answer was, is cardiac chaos normal or abnormal? Well, the outcome of this issue was basically, we cannot really assess whether the cardiovascular system is chaotic or not, because we have noise, we have stochastic components, and therefore we don't know if the trajectories diverge because of the stochasticity or because the system is chaotic. So these results were actually invalidated. So this is where we are now. We can consider the system as deterministic, and we know that there is some stochasticity, as I told you before, what we called physiological noise. Physiological noise that we must characterize. So the question is now, how do we characterize it? Well, first of all, we keep going with the assessment of the complexity. You can say, can we still talk about complexity if we say that it doesn't make sense? Well, chaoticity does not really make sense for the assessment in this kind of framework. Complexity still makes sense because we can define it as an extreme sensitivity to initial conditions. So we can still exploit the dynamical system theory and analyze a generic sequence of data points, so a time series, such that we account for a complexity assessment. First of all, we should better define which kind of stochasticity we are talking about. Well, as I told you before, we are not talking about the so-called measurement or output noise. This is not the stochasticity we are talking about. This is not what we define as a physiological noise. You see, this is what we define as an output or measurement noise. We have our system with an input and an output, and the measurement, the actual measurement, is contaminated by noise. In most of the modeling, this noise is additive to the output. And there are plenty of studies showing effective technique to suppress this noise and make this Y equal to 0, so to make an actual measurement. The noise we are talking about is dynamical. So physiological noise, as I told you before, here is this Wn, is an intrinsic part of the system. So you may consider a generic output of your system as a linear or nonlinear combination of the history plus this stochastic component. And this stochastic component changes for each time step, and this function of the history may be any continuous function, which of course is unknown. So you see macroscopically the difference. You have a sequence of noise, you have your intrinsic, let's say, output. This is the output noise. So when you have the sum of the noise and the output of your system, while this is the effect of dynamical noise. It's something that goes recursively into the system. So dynamical noise is what we define as physiological noise. Now, the scientific question that we may ask is the following. Let's say this is a physiological system. Let's say this is the cardiovascular system. We define an output, let's say the electrocardiogram or heartbeat dynamics. So how do we estimate, how can we say something quantitatively about this stochastic term without knowing something on the map? we don't know this function because, of course, if we know this function, whether it's a specific, for instance, nonlinear function, we may estimate this stochastic term by taking the residuals of our modeling with the actual data. And this is actually a very standard approach, but we don't know the system. So the deterministic part of the dynamics is totally unknown, can be linear or nonlinear, and still we want to characterize this stochastic term. Is that possible without any knowledge a priori? Well, the answer is yes, and we can do that by applying some information theoretic approach. The information theoretic approach that can be applied is called approximate entropy. And I have a few slides here to go in detail of the methodology, but I don't really, let's say, want to go in depth in the mathematics. I want you to grasp, let's say, the essence of this famous entropy. It's quite famous, although nowadays it has been sort of, let's say, substituted with what is called the sample entropy. Okay, so let's say we start from a time series, and the time series is the output of a system, and the system is the one that we want to characterize. The idea, the main idea behind this entropy is that we first reconstruct the phase space of the system through a methodology that is usually refers to the so-called Takens theorem. So the Takens theorem provides us with an estimate of the phase space, even if you don't know the constitutive equation of the system. So it gives you an estimate of the phase space considering delayed versions of the time series when they are arranged as vectors. The dimension of this phase space is called embedding dimension, while the time delay gives you the, let's say, resampling that should be associated with this vector. This is, let's say, very well-known literature for the field of nonlinear physics, and therefore I will not spend time on it. But just to say that from the time series, if we have a sufficient number of time points, we are able to estimate the phase space properly. Then for each point of the phase space, we want to count how many points are in a sphere of array R. So we define this region. Let's say if we are in 2 dimensions, we define a circle. And basically for each time sample, we see in the phase space how many others are in this circle. We take a normalized version of this counting. We sum the log of the values we obtained by normalizing it again for all the time samples of the phase space. And then we calculate this again by considering an additional dimension of the phase space. So you understand that being the approximate entropy being defined as the difference of this quantity when you have these 2 different dimensions of the phase space basically quantifies the level of predictability. So if the system is more predictable, then this difference tends to 0. And in fact, for regular systems, for regular dynamics, this is actually 0. While if the system is totally unpredictable, or if you want irregular, the series is irregular, like, by the way, the stochastic and the chaotic systems, then this approximate entropy reaches the maximum. And in fact, it's easy to demonstrate that the asymptotic maximum of this quantity is associated to the input being a realization of Gaussian random noise. So you may fix, the different parameters. Just to give you an example, for the heartbeat dynamics analysis, you may set the dimension of the phase space 2 or 3, and the radius of this circle as 20% of the standard deviation of the series. As I told you before, this quantifier has been quite successful for the characterization of habit dynamics, but there was an issue, and the issue is always the same. This is very sensitive to the underlying dynamical noise. In other words, if you have your data and you quantify a deviation of this guy, let's say between two groups, let's say a healthy and a pathological group, you don't know if the variation, which might be statistically significant, you don't know if this difference is due to a change in the underlying noise, so in the underlying stochasticity, in the underlying physiological noise, or it's due to a change in the dynamics, so to a change in the deterministic part of the system. And this kind of ambiguity cannot be resolved unless you estimate physiological noise, as by considering this kind of generic modeling. Again, I do remark that when you observe the time series, you do not know the deterministic dynamics. You are not, you can only hypothesize it. You don't know it, let's say, for sure. This is the approximate entropy as a function of the radius for exemplary logistic maps in a periodic regime for different levels of output and dynamical noise. You see that the dynamical noise increases, so the approximate entropy, increases as the noise increases, both in the regular or in the periodic regime. But you see that when there is no noise, when there is no stochastic noise, this profile is quite different. So a few years ago with my collaborators, we looked at these plots and we say, you know, from these plots, it seems quite evident, quite, let's say, straightforward to identify a noise-free or a noisy system, regardless of the dynamics in the periodic or chaotic regime. So we decided to explore how this approximate entropy profile changes in the physiological systems, and we actually came up with an estimation algorithm. We basically discovered that when you have a time series, which in general is the output of a deterministic system with some intrinsic stochasticity, and you get to the approximate entropy profile, you first assess if the system embeds noise, if the system embeds stochasticity. If it does, then we demonstrate with a theorem, which I will not go in detail to, we demonstrate that the value of the radius that actually coincides with the tangent line here of the minus log of the radius actually coincides with the stochastic, the variance, it actually coincides, with the standard deviation of the noise. Again, this is always true for any kind of deterministic dynamics underlying the system, okay? So with this theorem, we defined this estimation in a closed form, and this can be estimated for any distribution that you hypothesize being associated with the stochastic term. So in the subsequent works, what we did is to hypothesize that the underlying stochastic term has a Gaussian distribution. And from the time series, we estimated this stochastic term to see how it behaves in, let's say, real conditions. So what we did, first of all, was to analyze time series, so heartbeat dynamics from healthy and pathological subjects. In this particular study, we investigated data from structural recordings from normal subjects, patients with atrial fibrillation, and the patients with the congestive heart failure. And as you can see from this box plot, we showed that the intrinsic physiological noise associated to the cardiovascular dynamics is actually increased in pathologies. In particular, we have the atrial fibrillation is associated with the highest level of noise, statistically speaking, which might explain even 60 or 70% of the standard deviation of the original series. So it's quite an important component. Still, in congestive heart failure, we realized that there is an increased stochasticity, which may be in median around 50% of the standard deviation of the series. Then we estimated noise in the Fantasia dataset. This is a dataset in Physionet, which comprises heartbeat dynamic series from 20 subjects, can be elderly or young adults, while they watch the Fantasia movie. And you see here that our results highlights how the young adults are associated with an increased noise with respect to the elderly subject. So in other words, aging seems to be associated with a decrease in physiological noise of the cardiovascular system. This was a preliminary study that we ran in this dataset with a limited number of recordings. We replicated the studies by using the autonomic aging dataset. This is publicly available in Physionet as well, and the Lemon dataset. This is available in its own website. And with these two websites, with these two databases, we estimated noise in shorter series than these ones, but we got a quite large number of recordings, and we showed how for age groups from 18 to 85, more or less, year old, the noise tends to decrease. This is actually a regression line for the median levels of noise we get for each age group. So the results was pretty much confirmed. So cardiovascular noise, or if you want physiological noise in the cardiovascular system, when we consider heartbeat dynamics, decreases with aging. Then we move to neural dynamics. We perform some assessment in vitro and in vivo recording in mice, which showed that physiological noise in the neural systems, especially in the cortex, is unevenly distributed across the cortex. So there are brain regions that somehow are associated with higher stochasticity than others. And this is nice results that we got, because this was an in vivo recording in which each electrode, each channel was at a different depth of the cortex. So basically, these electrodes were more in depth, let's say, going down to the brain than these ones. So you see how the estimate of noise, our estimate of physiological noise, decreases almost linearly with the depth. So in other words, the more you go in depth, let's say in the subcortical region, the more noise, the more neural noise you find. So we applied the approach with the general, with the other kind of brain data, which is the EEG recordings. These are the results of a data set comprising 50 individuals performing, undergoing some resting state and some mental arithmetics. And these results confirm what we previously showed, so that the distribution of noise is different between regions. So there are regions that are more noisy, and actually, the most of the difference are in the occipital cortex. Regarding aging, in the Lemon dataset, we had EEG recordings other than the heartbeat dynamics. And we analyzed this series, and you see this is the median noise level across the group for different age ranges. You see that the noise clearly tends to increase with aging, and in particular tends to increase most of all in the temporal and the frontal region. So this is a clear result. Noise goes in median in the group from 30 to 40% of the standard deviation of the signal. So differently from cardiovascular dynamics, noise in brain dynamics seems actually to increase with aging, while in the cardiovascular system seems to decrease with aging. While this was a nice, let's say, number of individuals, we wanted to further investigate these results and see if this noise was, let's say, the results of the system because, let's say, of the measurement being performed over the skull, or this something that is associated also with the metabolic dynamic of the brain. Therefore, we analyzed a large data set of comprising recordings from healthy subjects at different age groups. This data was structural and fMRI data. The data that has been analyzed are the fMRI time series from the Human Connectome project and the so-called CAM-CAN datasets, where results were merged, and we got results from 1,745 individuals, and you see that the results are pretty much confirmed. So there is a different distribution of the correlation between the noise and age, and you see here that the color gets more intense, with the correlation being more, let's say, strong. And here you see the box plots that go with the different age groups. So these results confirm that, again, noise differently distributes across the brain regions, and it tends to increase with aging. So, in conclusion, dynamical noise is what we define as physiological noise, and it seems a quite significant characteristic of neurophysiological systems, especially because it may provide you with an assessment of complementing the so-called complexity assessment. So this kind of noise biases your assessment, so the assessment is meant to better characterize your system. We showed how this noise is modulated by so many states, scales, so at the level of the neuron, at the level of the cortex systems, etc., and is modulated also by tasks or the stimuli. Concerning aging, we observe that physiological noise in the cardiovascular systems tends to decrease with aging, while physiological noise in the brain tends to increase with aging. Well, we are currently working in trying to understand what are actually, so why we have this difference and what can actually be associated with the more details of the ions and the other dynamics of this physiological noise. And methodologically speaking, we are working on a multivariate estimation of noise. So when you consider a multivariate system, and therefore you may characterize the noise in terms of covariance matrices. I thank my collaborators for the contribution of this work, and I thank you very much for the attention.
Wonderful. Thank you so much, Dr. Valenza, for a very interesting and engaging talk. At this point, we have a little bit of time for Q&A. And if people in the audience have any questions, you can raise your hands and we can unmute you so you can ask a question. Or you can type in your questions in the Q&A box in Zoom, whichever method you prefer. And while we wait for people to type in their questions, if they have any, I have a quick question from you. Very interesting results about both EEG and also cardiovascular noise. The question I have is about physiological noise that you found in cardiovascular system, then that your results and findings showing that it reduces with aging. Do you know what the underlying mechanism would be, or how do we interpret this result? What is the cause and mechanism for this?
Thank you for the question. We are working on it, and we believe that it's something that may be related to the concurrent action of the sympathetic and the vagal activity. But still, this is something that we do not know for sure. And it's actually very difficult to assess in humans because we don't have this kind of, let me say, precise recording. So we are also engaging in some study in animal models to actually understand what it can be related to.
So the hypothesis is that the similar trend would be observable in rats or mice, or?
Yes, of course, the hypothesis is that the dynamics are similar, and we have some clue about, macroscopic behavior of heartbeat dynamics. The animal models will give us, let's say, the possibility to study the proteins that are involved in the transmission of the signal throughout the body. Just to give an example, they are the so-called piezo proteins, which are basically the mechanoreceptor, and they are used to have closed loop information regulation of blood pressure, which in turn regulate heartbeat dynamics. So one hypothesis is that they can be linked to this stochasticity, but we don't know.
Yeah. People in the audience, if you have any questions, feel free to jump in or raise your hands or type in your questions. But I have a quick follow-up question. So for the noise that you estimate in brain activity, do you relate that to measurement noise or actual reduction in noise, inherent noise in I don't know what activations, or I'm not sure what.
As as I said, we do not refer to measurement noise.
Mhm.
So measurement noise is something that, of course, bias the assessment, but is not something that we consider as a physiological noise. So measurement noise is removed with the standard pipeline for processing. And as you know, in those kind of series, in the fMRI series, is quite, let's say, well-defined approach, especially the big and large data sets that are available online. So that noise is considered to be removed, or at least, let's say, comparable with other studies. What we quantify is the dynamical one, the intrinsic one, also recursively. Yeah.
Okay, very good. Thank you very much. Thank you for clarifying answers. Are there any questions from the audience? If not, we are approaching 1 o'clock. It's 12:59, and I understand that people might have other meetings coming up, and especially our speaker. Okay, let's collectively thank our speaker with a final virtual round of applause. Thank you again.
Thank you. Thank you very much.
And thank you also people in the audience for joining me.
Have a nice day.
Yeah,
Bye-bye.
you too. Thank you again, and sorry about the trouble.